Hello everyone, this is Sister Celestine, Assistant Professor, Department of Mathematics, St. Joseph's College of Arts and Science for Women. In this video, we are going to see small sample tests. In that small sample test, specifically, we are going to find the F test for equality of two population variances. That is, for suppose we want to test the two independent samples which have been taken from the normal populations, but that is they both are having the same variances sigma squared. Okay, the two independent samples we are naming as xi where I is equal to 1 to n1 and yj where j is equal to 1 to n2. Okay, now what we are doing means whether these two independent samples we are taking for these samples we are taking the estimates whether those estimates of the population variance are homogeneous or not, we are going to find out. Okay. Now, under the null hypothesis, we are saying that sigma x squared, that is the variances of the first normal population and variances of the second normal populations are equal, and it is denoted as the same normal population variance sigma squared under the null hypothesis, that is the population's variances are equal. And the second point is two independent estimates of the population variance. For these two population variances we are taking independent estimates, then they both are equal, that is we are telling as f equal to sx squared by sy squared, where sx squared is equal to 1 by n minus 1 into summation xi minus x power the whole square. Sx squared is nothing but the degrees of freedom. Okay, so degrees of, sx squared is nothing but the variances. So summation xi minus x power the whole square divided by n minus 1, n1 minus 1, and sy squared is also the summation sigma yj minus y bar the whole square divided by n2 minus 1. This is the chi-squared this is the unbiased estimates of the common population sigma squared obtained from two independent samples, and it follows Snedeker's F distribution. We told this is Snedeker's F distribution. Snedeker's F distribution is nothing but the ratio of the two independent chi-square variates divided by their respective degrees of freedom, where the degrees of freedom are v1 and v2, that is v1 is equal to n1 minus 1, v2 is equal to n2 minus 1. Okay, now we'll go to see the proof. F equal, in the definition itself we have seen f equal to sx squared by sy squared. So there we have seen what is sx squared and sy squared, isn't it? Okay, sx squared is equal to sx squared is equal to 1 by n minus 1 into summation xi minus x bar the whole square, as well as this is yj minus y bar. Okay, now we'll see. Okay. We know that sample for the samples we are taking the variances small s x squared equal to 1 by n1 into summation xi minus summation xi minus x bar the whole square. Likewise, small s y squared is equal to 1 by n2 into summation yj minus y bar the whole square. Okay, so this is the variance for the samples xi and variance for the sample sy. Okay, so instead of that is summation xi minus x bar the whole square, we are writing this one, that is we are taking this n1 to this side. Okay, so which is equal to n1 into small s x squared. Okay, likewise for this yi minus y yj minus y bar the whole square. For this yj minus summation yj minus y bar the whole square, we are writing this one. This we taking this n to this side, which is equal to n2 divided by s small s y squared. Okay, these two only we are substituting here, n1 sx squared, n2 sy squared. But we know that f is nothing but the ratio of the chi-squared variate. Ratio of the chi-squared variate. Chi-squared variate is nothing but the square of the normal variate. Okay, normal standard normal variate is it okay, square of the standard normal variate. Okay, standard normal variate is equal to summation. Okay, x minus. Okay, standard normal variate is nothing but summation. Okay, xi minus mu divided by sigma. Okay, xi minus mu divided by sigma the whole square. So this format we want. We have this format. Okay, wow, xi minus mu. Okay, here mu is x bar. Okay, so this format we have n1 is x squared is equal. We have n1 is x squared. We have okay, and f distribution is chi-squared variate ratio of the chi-squared variate by with the normal distribute the degrees of freedom. So degrees of freedom also we have in this. What is lacking? The sigma is lacking. Okay, that means here for this sigma x squared and for this sigma y squared. So what I am doing is to get the independent chi-square variate, I am multiplying. Okay, wow, multiplying and dividing the sigma x squared here, and I am multiplying and dividing the sigma y squared here. Okay, sigma y squared here. Okay, if I do sigma x squared, here also sigma x squared will come. Okay, and here also sigma y squared will come. Okay, in the first itself we have told. Okay, in the first itself we have told under the first itself told under the null hypothesis. Okay, sigma x is under the null hypothesis, sigma x square equal to sigma y square equal to sigma square. We are using that one here. So this both are equal under the null hypothesis. This is in the numerator and this is in the denominator. So the sigma x square and the sigma y square will be get cancelled. Okay, then we get this one. Then we get n1 is x squared divided by sigma x squared into 1 by n1 minus 1. Here n2 sy squared divided by sigma y squared into 1 by n2 minus 1. Here this one n1 is x squared by sigma x squared. This is the chi-square variate, and n2 sy squared sigma y squared is also the chi-square variate, and they are by the degrees of freedom n1 minus 1 for this, and here for n2 minus 1. This is in the form of chi-square variates ratio of two independent chi-square variates. Okay, divided by the degrees of same degrees of freedom. So this is follows the F statistic. Since n1 is this and this are independent chi-square variates with n minus 1 and n2 minus 1 degrees of freedom respectively, then F follows the Snedeker's F distribution with the n1 minus 1 and n2 minus 1 degrees of freedom, we can say. Okay, now what we are going to using this, we are going to see an example. Okay, pumpkins were grown under two experimental conditions. Okay, here we told two population variances. The two population variances here, two experimental conditions. From that we are taking two random samples of 11 and 9 pumpkins. Show the sample standard and the sample standard deviations of their weights are 0.8 and 0.5, assuming that we are assuming the weight distributions are normal, test the hypothesis that the true variances are equal against the alternate. Okay. They themselves told that the true variances, that is, under null hypothesis, they are equal, and alternative hypothesis, they are not. So this is a two-tailed test at the 10 percentage level. That also they have given, and probability of f of 10 comma 8 is these two values is also they have given. Now we want to test the null hypothesis. Okay, true variances are equal, they told. So we are taking under null hypothesis sigma x squared and sigma y squared are equal. Against that they are not, they told. So against the alternative hypothesis, we are defining the alternative hypothesis as h1 equal to sigma x squared, which is not equal to sigma y squared. Since it is not equal to, so we are telling this is two-tailed equation. So, and also we are given number of pumpkins, n1 equal to 11 and n2 equal to 9. And standard deviation also they have given sx equal to 0.8 and sy equal to 0.5. Okay, so under the null hypothesis, h naught equal to sigma x squared equal to sigma y squared. The statistics we know f equal to capital Sx squared by sy squared follows f distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Okay, we know that Sx squared equal to, we know the formula Sx squared equal to, okay, by we are seeing here Sx squared equal to this one. So from this one we are writing as n1 Sx squared. So Sx squared is equal to this Sx squared, this Sx squared we can write it as capital Sx squared is equal to n1 small sx squared divided by n1 minus 1. Okay, n1 minus 1. Likewise, sy squared equal to n2. Okay, so first n1 is x squared equal. So this one I am here they have given us this n1 minus 1 they have taken this side. N1 minus 1 they are taking this side and they are writing n1 minus 1 into capital S x squared, which is equal to small n1 sx squared, small sx squared. Okay, well, that one we are writing. So now they are taking this n1 to this side as a denominator. So n1 by n1 minus 1 into sx squared. Okay, n1 they have given n1 they have given 11. So using that we are writing n1 is equal to n1 is equal to 11. Here n1 minus 1, so 10. Sx also they have given 0.8, so 0.8 the whole square. So if I do the calculation, then I am getting the value 0.704. Okay, similarly sy squared also they have given n2 is equal to 9, so n2 minus 1 8 and sy also 0.5. So we are getting this value. So f value is sx squared by sy squared. If I divide, I will get 2.5. The significant values of f for two-tailed test at level of significances, the size of the significance that also they have given 10%. So alpha equal to 0.10. So f is greater than f alpha by 2 is equal to f alpha by 2 equal to this one we are dividing by 2. So if we are dividing by 2, we will get 0.05. Okay. Then we are telling f is greater than, since it is two-tailed test, for two-tailed test f should be greater than, for the f alpha, f should be greater than f alpha by 2 and f is less than 1 minus f of 1 minus alpha by 2. This is for two-tailed test condition. This is condition for the two-tailed test. Okay, well, now we'll see. And the next one, we are given the tabulated significant values. They themselves are given, that is probability of f 10 comma 8 greater than or equal to 3.35 is equal to 0.05 they have given. So that is f of 0.05 value is 3.35. That we are taking as equation 1. Also they have given f of 10 comma 8 means this one, and 8 comma 10 means 10 is degrees of freedom, n1 minus 1, 8 is degrees of freedom, n2 minus 1. So, f of degrees of freedom, n1 minus first degrees of freedom, comma second degrees of freedom, which is greater than or equal to 3.35, then only we can get alpha by 2 0.05, they themselves have given. So, by that we are taking f of n1 minus 1, comma n2 minus 1 of alpha by 2 is equal to 3.35. Also, they have given if we take n2 minus 1, n1 minus 1, which is greater than equal when we get the alpha by 2 is 3.07. Okay, that also we are taking. Okay, now we want to the 1 minus alpha by 2. That's why we are taking this. We are dividing there, we are taking the reciprocal of this. So 1 by f of f 8 comma 10. So when we taking the reciprocal, this greater than or equal to will become the less than or equal to. So 1 by 3.07 equal to 0.5. So if I dividing this one, yeah, you can get 0.326 equal to 0.05. That is probability of f 10 comma 8 is greater than or equal to 0.326 equal to 0.195. 0.95. Okay, that is if we write f of 10 comma 8 of 0.95. 0.95 is nothing but our 1 minus alpha by 2. Okay, this is nothing but our 1 minus alpha by 2. Okay, that value which is equal to 0.326. 0.326. This is our third equation. So from this one, that is two-tailed test condition, and from this two given the f value, and from this three, that is 1 minus alpha by 2, we can get the critical values for testing h naught. The critical values for testing h naught equal to sigma x square equal to sigma y square against h1 equal to sigma x square not equal to sigma y square. At level of significance alpha equal to 0.10 is given by f will be greater than 0.335, otherwise f will and f is less than 0.33. Okay, 0.326 is 0.33. Since the calculated value we have calculated here, f is 2.5, it is greater than this value, less than this value, greater than value is 3.35, less than value is 3.3. So this 2.5 is lies between these two and it is not significant, and hence the null hypothesis of the equality of populations variances may be accepted at level of significance alpha equal to 0.10. Okay, that we can say. Thank you.